Grounding and bonding are essential components of electrical systems, crucial for safety and proper operation. Grounding provides a path for fault current to return to the source, allowing overcurrent devices like circuit breakers or fuses to trip, thereby preventing electrical shock hazards and minimizing equipment damage. Bonding, on the other hand, ensures that all metallic parts of an electrical system are at the same electrical potential, further reducing the risk of shock. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding to ensure electrical safety. Let's delve deeper into the concepts and requirements. Grounding refers to connecting the electrical system to the earth, establishing a reference point for voltage. This is typically achieved through a grounding electrode system, which can consist of things such as a ground rod, ground plate, or connection to a metallic water pipe. The grounding electrode conductor connects the grounding electrode to the system's neutral point, typically at the service entrance. The purpose of grounding is multifaceted. Firstly, it stabilizes voltage to earth, reducing voltage stress on insulation. Secondly, it provides a low impedance path for fault current, facilitating the operation of overcurrent protective devices. Thirdly, it limits voltage rise due to lightning strikes or other transient overvoltages. There are two main types of grounding systems: system grounding and equipment grounding. System grounding involves grounding the neutral conductor of the electrical system, while equipment grounding involves grounding non-current carrying metallic parts of equipment and enclosures. Bonding, in contrast to grounding, focuses on creating an electrically conductive path between all metallic parts of an electrical system. This includes things like metal conduits, enclosures, and equipment frames. The purpose of bonding is to ensure that all these metallic parts are at the same electrical potential. This minimizes the voltage difference between them, reducing the risk of electrical shock if someone comes into contact with two different metallic parts simultaneously. Bonding is achieved through bonding jumpers, which are conductors that connect the metallic parts together. These jumpers can be made of copper or other conductive materials. The size of the bonding jumpers is determined by the size of the circuit conductors. Several key components contribute to effective grounding and bonding. Firstly, the grounding electrode conductor connects the grounded conductor, usually the neutral, to the grounding electrode. Its size is based on the size of the service entrance conductors according to NEC Table 250.66. Secondly, the equipment grounding conductor provides a low impedance path for fault current from equipment back to the source. It is sized according to NEC Table 250.122, based on the rating of the overcurrent protective device. Thirdly, bonding jumpers connect metallic parts of the electrical system to ensure electrical continuity. Their size is also determined by NEC tables, ensuring they can safely carry fault current. The NEC provides comprehensive guidelines for grounding and bonding, addressing various aspects of electrical system design and installation. NEC Article 250 is dedicated to grounding and bonding requirements. It covers topics such as grounding electrode systems, grounding conductor sizing, bonding methods, and specific requirements for different types of equipment and systems. Some key NEC requirements include ensuring a low impedance ground fault path, proper sizing of grounding and bonding conductors, and effective bonding of metallic enclosures and equipment. The NEC also addresses specific grounding and bonding requirements for sensitive electronic equipment to minimize noise and interference. Some common grounding and bonding mistakes include improper sizing of grounding and bonding conductors, inadequate bonding of metallic enclosures, and failure to properly connect the grounding electrode system. These mistakes can compromise the effectiveness of the grounding and bonding system, increasing the risk of electrical shock and equipment damage. Regular inspection and testing of grounding and bonding systems are essential to ensure their effectiveness. Testing methods include things such as ground resistance testing, continuity testing, and visual inspection of connections. Ground resistance testing measures the resistance of the grounding electrode system to earth. Continuity testing verifies the electrical continuity of bonding connections. Visual inspections can identify loose connections, corrosion, or other signs of deterioration. Effective grounding and bonding offer numerous benefits. Firstly, they enhance electrical safety by reducing the risk of electrical shock. Secondly, they protect equipment from damage caused by fault currents. Thirdly, they improve system reliability by providing a stable voltage reference. Fourthly, they minimize electrical noise and interference, ensuring proper operation of sensitive electronic equipment. Grounding and bonding are critical for various applications, including residential, commercial, and industrial electrical systems. In residential systems, grounding and bonding protect occupants for electrical shock hazards. In commercial buildings, they protect equipment and ensure business continuity. In industrial facilities, they protect workers and prevent costly downtime. Let's consider some practical examples. Firstly, in a residential wiring scenario, the grounding electrode conductor connects the neutral bus in the service panel to a ground rod driven into the earth. Bonding jumpers connect metallic water pipes and gas pipes to the grounding system. Secondly, in a commercial building, the grounding system may include a combination of ground rods, ground plates, and connections to the building's steel structure. Bonding jumpers connect all metallic conduits, enclosures, and equipment frames. Thirdly, in an industrial facility, the grounding system may include a dedicated grounding grid buried beneath the facility. Bonding jumpers connect all metallic equipment and structures to the grounding grid. The grounding electrode system typically consists of one or more grounding electrodes connected to the earth. Common types of grounding electrodes include ground rods, ground plates, and metallic water pipes. Ground rods are typically made of copper or copper-clad steel and are driven vertically into the earth. Ground plates are typically made of copper or steel and are buried horizontally in the earth. Metallic water pipes can be used as grounding electrodes if they meet certain requirements, such as being in direct contact with the earth for minimum length. The grounding electrode conductor connects the grounding electrode to the system's neutral point. Its size is based on the size of the service entrance conductors, as specified in NEC Table 250.66. The grounding electrode conductor must be securely connected to the grounding electrode and the neutral point. The equipment grounding conductor provides a low impedance path for fault current from equipment back to the source. It is typically a copper or aluminum conductor and is run along with the circuit conductors. The size of the equipment grounding conductor is based on the rating of the overcurrent protective device, as specified in NEC Table 250.122. The equipment grounding conductor must be securely connected to the equipment and the grounding bus in the panel board. Bonding jumpers are used to connect metallic parts of the electrical system to ensure electrical continuity. They can be made of copper, aluminum, or other conductive materials. The size of the bonding jumpers is determined by NEC tables, ensuring they can safely carry fault current. Bonding jumpers must be securely connected to the metallic parts being bonded. Proper installation of grounding and bonding systems is crucial for their effectiveness. This includes ensuring proper connections, using appropriate materials, and following NEC guidelines. Connections must be tight and corrosion resistant to ensure low impedance. Materials must be compatible with each other to prevent corrosion. NEC guidelines provide detailed requirements for grounding and bonding in various applications. Regular inspection and maintenance of grounding and bonding systems are essential to ensure their continued effectiveness. This includes visual inspection of connections, testing of ground resistance, and testing of continuity. Loose connections, corrosion, or other signs of deterioration must be addressed promptly. Ground resistance testing measures the resistance of the grounding electrode system to earth. A low ground resistance is desirable to ensure effective grounding. The ground resistance should be measured using a ground resistance tester, which applies a test current to the grounding electrode and measures the resulting voltage drop. Continuity testing verifies the electrical continuity of bonding connections. A low resistance reading indicates good continuity. Continuity testing can be performed using a multimeter or a specialized continuity tester. Troubleshooting grounding and bonding problems requires a systematic approach. This includes visually inspecting connections, testing for voltage, and testing for continuity. Loose connections, corrosion, or other signs of deterioration should be addressed. Voltage testing can identify problems such as open grounds or voltage on equipment enclosures. Continuity testing can identify broken or disconnected bonding jumpers. The NEC provides specific requirements for grounding and bonding in different types of occupancies, such as residential, commercial, and industrial. These requirements are tailored to the specific hazards and electrical systems present in each type of occupancy. For example, the NEC may require additional grounding electrodes in industrial facilities with large electrical loads. It is essential to consult the NEC to ensure that grounding and bonding systems comply with the applicable requirements for the specific type of occupancy. Grounding and bonding play a vital role in protecting sensitive electronic equipment from damage and ensuring its proper operation. Sensitive electronic equipment is susceptible to damage from voltage surges, electrical noise, and other disturbances. Grounding and bonding provide a low impedance path for these disturbances, diverting them away from the equipment. The NEC provides specific requirements for grounding and bonding of sensitive electronic equipment to minimize noise and interference. These requirements may include the use of isolated ground receptacles, dedicated grounding conductors, and shielded cables. Surge protective devices, or SPDs, are often used in conjunction with grounding and bonding to protect sensitive electronic equipment from voltage surges. SPD are designed to divert surge current to ground, preventing it from reaching the equipment. In summary, grounding and bonding are essential components of electrical systems, crucial for safety, equipment protection, and system reliability. Understanding the principles, requirements, and best practices of grounding and bonding is essential for anyone involved in electrical design, installation, or maintenance. By following the NEC guidelines and implementing proper grounding and bonding techniques, you can ensure a safe and reliable electrical system. Furthermore, continuous education is crucial for staying updated on the latest advancements in electrical safety and grounding and bonding practices. Reviewing industry publications, attending workshops, and participating in training programs can help you enhance your knowledge and skills in this critical area. Remember that electrical safety is a shared responsibility. By prioritizing grounding and bonding, we can create safer environments for ourselves, our families, and our communities. The NEC is regularly updated to reflect changes in technology and best practices. Staying current with the latest edition of the NEC is essential for ensuring compliance in electrical safety. Changes to the NEC can impact grounding and bonding requirements, such as conductor sizing, electrode placement, and bonding methods. It is important to review the NEC updates and understand how they affect your work. Grounding and bonding are not one-size-fits-all solutions. The specific requirements and techniques may vary depending on the application, the type of equipment, and the local electrical codes. It is important to consult with qualified electrical professionals and engineers to design and install grounding and bonding systems that meet the specific needs of your project. They can assess the unique challenges and provide tailored solutions that ensure safety and compliance. Effective communication is key when working on grounding and bonding systems. Clearly label all grounding and bonding conductors and connections to avoid confusion. Document the grounding and bonding system design and installation details for future reference. Share information about grounding and bonding practices with other stakeholders such as building owners, facility managers, and maintenance personnel. A well-documented and communicated grounding and bonding system can facilitate troubleshooting, maintenance, and future modifications. Continuous improvement is essential for maintaining a safe and reliable electrical system. Regularly review and evaluate your grounding and bonding practices to identify areas for improvement. Seek feedback from electrical professionals, conduct audits, and analyze incident reports to identify potential weaknesses. Implement corrective actions and preventive measures to address any identified issues. By embracing a culture of continuous improvement, you can enhance the effectiveness of your grounding and bonding systems and minimize the risk of electrical hazards.